Is this the right scheduling algorithm for my Mac? How do we decide if something's the right scheduling algorithm for some computing system? So we got to think about what people are doing with it and what our goals are. If what we're doing with a Mac is running things like typical users do, maybe you're running better things than I am. You're running processes like this. Do you want preemptive priority scheduling, or do you want something else? So do all processes have the same needs? You might have some processes that are doing a lot of computing, like my RWR counter program, which I think has finished running. You have some that are doing very little, but you want to be very responsive, right, if a user is interacting with them. Probably every program, when a user interacts with it, you want it to be responsive. You have others that are doing things like playing video, where they have real-time requirement. You have each frame rendered at the frame rate, but giving them more resources than that isn't useful. So you've got lots of different kinds of processes. If you want a scheduler to give a user a good experience and use resources well, it shouldn't treat all processes the same. Priority is not really enough to tell you how to do scheduling. It tells you something, but it doesn't help you distinguish, especially between these kinds of processes and these kinds of processes. So the compute-bound processes probably should have low priority. They're not something the user's waiting for, but you do want them to finish. The I/O-bound processes, well, those should have high priority when the user's using them, but otherwise probably aren't doing anything. So maybe they can have high priority most of the time. Although if you look at the priorities of the processes running on my Mac, most of the user interacting processes are not given high priority. The ones that are actually high priority are things that I would think should be background processes, like the MD worker. You want something somewhat more sophisticated than just priority preemptive. You want to treat different processes. We're going to look soon at what Unix actually does. Let me tell you about two other scheduling algorithms that are both part of Carl Waldsberger's PhD. I mentioned the quote from Paul Graham a few classes ago about Robert Morris finding a way to get out of grad school without writing a dissertation. This is one of the few examples of a dissertation that's actually widely read and is well worth reading. It introduced these two kinds of scheduling. One is lottery scheduling. The idea of lottery scheduling is you allocate tickets to processes, and what the scheduler does at each time slice is randomly pick a ticket and let that process run. This gives you a way to allocate priority. You can give different processes different numbers of tickets. Makes scheduling very simple. All the scheduler is doing is randomly picking from a ticket. But it also gives you a system that processes can use to distribute their share. Process can give its tickets to another process. If you want to have some other process do work for your process, you can allocate tickets to it. It gives threads away to control how their share is used. How do we like this compared to priority preemptive? Does this do better on resource usage than priority preemptive? Well, not really, right? It's still following the model of the scheduler runs periodically, and each time it runs, it picks some new process to run. As long as you're doing that, you're doing a lot of switching. This is not doing anything to reduce the amount of switching that priority preemptive would do. In fact, it's probably doing more, because it's randomly picking which one to run. How does it do as far as fairness? Is this more or less fair than priority preemptive? So one of the things we said we didn't like about priority preemptive is if there's enough high priority processes to keep the CPU busy all the time, the low priority processes never get to run at all. Does the lottery scheduling have that property? Stand up. If people aren't going to answer a question like this, then I need to give you some exercise. Do you have room to do jumping jacks? Maybe not. You have room to at least jump up and down, even if you can't do your arms. So go ahead and jump up and down. Good job. Okay. Okay. Okay, good. You got your exercise a little bit. Maybe you're awake now. You can keep standing if you want. How does this do on fairness compared to priority preemptive? Good, yeah, so a high priority task might get really unlucky. I should put guarantee in quotes. Priority preemptive gives this guarantee that the highest priority will get to run. The lottery scheduling, there's no guarantee. You're randomly picking which one to run. It might pick the lowest priority task to run and keep picking low priority tasks. So in that sense, the priority preemptive is more fair. In terms of the starvation problem, does it have the starvation problem that we had with the priority preemptive? Good, yeah, so it does give you this control that you can share tickets. It also gives you at least a probability you're going to get some share eventually. Priority preemptive guarantees that these low priority processes never run if the high priority processes are there. The lottery scheduling, everyone's got some probability to run. So if you wait long enough, everyone's going to get to run, even if the high priority process always have something to do. That's the advantage. And it also has a big advantage. It's really simple to do. Right? You just randomly pick and it gives you this control of sharing tickets. But if you don't like this guarantee, the lack of the guarantee, which is a pretty big deal, not having a guarantee of any kind of predictability about getting the high priority processes to run, the other scheduling algorithm that was part of this dissertation was stride scheduling. And stride scheduling gives you pretty much the same level of flexibility as loitering scheduling. You can share tickets in the sense you can give processes whatever priority you want, but with a guarantee. And the way stride scheduling works is really simple as well. You're giving each process a stride, and the stride is the time. So this is the stride. Let's say it's 12 for this process. So you've got some counter you can think of the processor having. Once your stride is passed, you're going to pick from all the ones who are ready to run, whose stride is passed, you're going to pick the minimum one, and that one's going to run. And then once a process runs, the next time it's going to run, so this is the pass value. Once the process runs, its next pass value increases by its stride. So it won't run again until that stride is passed, and then once that time is passed, it's going to have highest priority to run. So this gives you a lot of flexibility and a lot of control. So we talked about the desired goal of the scheduler in terms of using resources. We also want to limit the time it takes to do scheduling. So what is the running time of a stride scheduler? How much work does the scheduler have to do? The main thing it has to do, right, is in this allocate. Right? This is what happens every time the scheduler gets called. It's deciding which process to run. It's picking a task from this task queue. How much work is that? So what are the expensive things in this allocate? What are the expensive operations that it's doing? Selecting, okay, so which line of code is that? Okay, so they remove from the queue. This is selecting the minimum client. Pass has gone to here, and we're looking for a client that has passed its stride. How expensive do you think that's going to be? We're not looking at the code for those. Depends a lot on the data structures we use. One of these is going to be expensive. So we could keep the queue sorted, and finding the minimum is going to be constant time, but then insert's going to be expensive. We could keep the queue in some other way. If we didn't sort the queue at all, finding the minimum is going to be linear time looking through the whole queue. But if we keep it sorted, how does the cost scale with each lookup? Yeah, so the cost of one of these is going to scale with the log of the number of processes. If we keep it sorted, the insert's going to take log n time. If we don't keep it sorted, well, then finding the min is going to take linear time. We're not going to do better than log n time. Should this worry us? How big is n? It's just the number of processes. We can have thousands of processes. Probably not millions, at least not on normal machines today. So do we care about log n when n is less than 1 million? Not unless we're a theory person. For n less than 1 million, log n is some small constant. Right? That's going to be less than 20. So that's not a big problem that it takes log n work. On my Mac, at least, the max process ID is 32,000. You could configure that to be higher, but it's rare to have more than a few thousand processes running. I'm not going to be able to finish scheduling Linux, but I want to talk about this a little bit today, and then we'll continue next time. So this is what the Linux scheduler is doing before 2002, a little more than 10 years ago. It had 3 types of processes. So we had normal user processes, non-preemptible, and real-time. Does that make sense given what we've talked about? People wanting to do on their laptop have those 3 types of processes. The things that normally would be real-time are things like video players that have a real-time constraint. Parts of the kernel are running non-preemptible. It's not a fully preemptive operating system in the sense that there are tasks that run that can't be preempted. Only kernel-level processes can do that. User-level processes can be preempted. The way the scheduler would select the next process is to use a goodness function to pick the best process to run. And what that function would do is use those priority values and other things to figure out which one to run. We will continue with this next class. Stride scheduling actually works pretty well. Most people don't really run a scheduler to figure out what to do, but you're sort of running one in your brain or in your to-do list or otherwise. Most people tend to focus on priority preemptive. Whatever higher priority task comes in, you interrupt whatever you're doing, and you spend all your energy on that and not on other things. That's probably better than at least the first come, first serve or earliest deadline. But I would encourage you to try stride scheduling.